Alrighty, good afternoon, everybody. It's Mr. Motorhone again, doing one of my lectures to try to teach you guys the best I can from a distance. And I'm hoping that this lesson is a little bit of a review because I believe you have seen some of these rules before, either in middle school or last year, for those of you who took Integrated 2. And remember a little bit of this information. So we know that we're talking about exponential functions. And so we've already done a lot of the modeling. Earlier in the week, I showed you how to find the equation, one of the model equations from either a point or the intercept and stuff like that. So I also want to take some time to review some of the properties of exponents because they could come back later when we're either solving or trying to simplify certain equations, because that's our last step. So let me go over some of the rules with you. So the good news is there's primarily, there are little exceptions and little things like that, but there's primarily three major rules that are going to get you through these problems. So I wrote them out here ahead of time. One is called the multiplication rule, and as you can imagine, we're going to recognize it based off when we see multiplication in certain problems. There is also the division rule, and again, to no surprise, we're going to recognize that we need it when we see division in a certain problem. And lastly, we see the power rule, and we're going to notice that we will need it when we have a certain power. And so what I'm going to do is I'm going to model each of these rules with a very similar example, but slightly altered each time. So here's the first example. So in the blue for multiplication rule, I'm going to say, let's say that we had something like x to the third power times x to the fifth power. Okay, something along those lines. So for those of you who understand the basic idea of an exponent, pretty much what this is saying is, if we treat each of these separately, the orange is saying there are 3 copies of the x variable, and the x to the fifth is saying there are 5 copies of the x variable. So is there a way that we could potentially write that in a more simplified, more straightforward, less roundabout way? And so if we just do a little bit of counting, we could see that we could write it as 1 copy, 2 copies, 3 copies, 4 copies, 5 copies, 6, 7, 8 total copies. So we see that even though we started off as 2 separate things, we can combine all of this into one simplified expression, which is x to the 8th power. Okay, so that's the most simplified way. Now, this is a very straightforward example, but you can imagine with bigger numbers, or just if this type of property were embedded in a bigger problem, that it might be useful to have a shortcut to arrive at this answer rather than writing out everything over and over and over. So I mean, like, let's say I had x to the 21st power times x to the, 48th power, right? You don't want to sit there and go x over and over and over, right? You're going to spend your whole day writing x's for a really, really long time, and then you're going to probably miscount, or you're going to draw not enough or too many, and then it's just going to become a big struggle for you. So part of my point today is to give you some shortcuts or some strategies that you can use to make some of these seemingly complicated variable expressions a little bit easier. So let's go back to the original question, and let's pay attention to their powers. So if we look at the powers, we'll see we had a 3 and we had a 5. And we ended up with an 8. So then my question to you is, how can 3 and 5 make the number 8? So think about that. And, you're thinking, and you're like, okay, could addition be an answer? Could subtraction lead me to the answer? Could multiplication lead me to the answer? Could division lead me to the answer? And I think most of you will be able to see that if I just added, right, those two numbers, then I would be able to get 8 very easily. So if I was kind of going for this more straightforwardly, I would say we could say x to the third times x to the fifth is x to the 3 plus 5, which would give you the value 8. Okay, so if I wanted to write this a little more generally, let me extend this line real quick. I would say something like this. So this is the multiplication rule. So what it says is, if you have the same variable, so x times, that's why it's called multiplication. In fact, let me write that in blue since the whole color of this is blue. So times x, right? So notice that I wrote the same letter. It only works if you have the same letter. If you have y's, then you got to do y's. If you have x's, you got to use x's. But you cannot bridge two different letter families together using this rule. And so if I had 3 for one, and if I had 5 for the other, the rule is saying I could say x to the 3 plus 5. Okay, so the general rule would look something like this. X to some power, okay, so that A represents any power, times same variable, x, to another power, we'll call this one B, is going to be equal to, again, same letter, that letter never changes, but we're going to add the powers together. So A plus B. So this is what we call the multiplication rule. And it's actually very important that we are reviewing this because we're going to see in a couple weeks towards, the end of the school year, maybe mid-May, in about 2 weeks or so, we're going to study another type of function related to exponents, and it's going to have similar properties. Okay, so that is the multiplication rule. Sorry. Okay, now let's move on to the division rule. So what's a good example of something that would use the division rule? We could have something like x to the 10th power divided by x to the 4th power. And if I do that, let me see, oh dang it. Okay, so if I do that, I'm going to notice that I have, what does it mean to have a power of 10? It means I'm going to have 10 copies. So 1, 2, 3, 4, 5, 6, 7, dang it, 8, 9, 10. Sorry, I know that's not the best, but I tried. So there's 10 copies on top, and if I look on the bottom, there are 4 copies. So 1, 2, 3, 4. And hopefully at some point in your previous, earlier math education, maybe in a younger grade, you learned what happens when we divide a number by itself. So I'll go over here, quick side note. So note, let's say you had 3 times 5 divided by 7 times 5, right? Well, I know at the, I forget exactly when I did it. At some point last semester, I was writing little ones like this, right? Because I was trying to show you that in certain cases, when you have the same number on the top and bottom of a fraction, they pretty much simplified to 1. So another way that I could write this specific multiplication problem is I could write it as 3 over 7 times like a big 1. And anything times 1 is equal to itself, right? So you're pretty much getting rid of the factors or the multiplications that just make the number bigger, the fraction bigger, but it's not the most simplified or the most reduced version of the fraction. So if we get rid of these 5s, right, if we just think of them as a big value 1, then the simplified way is to say just 3 over 7. So that would be the simplified way. Now here in this example, we have letters, not numbers, but if we just imagine the letter replaces or takes the space of a number, we could do something very similar. So I'm going to go ahead and highlight the pairs. So I have one pair, I have one pair, so that's one pair. I have 2 pairs. I have 3 pairs. I have 4 pairs, right? So you'll notice that I have 4 copies. Let me see. So I have 4 copies. Oh, yellow's not a good color. Let's try this. Yeah, there we go. So I pretty much have 4 copies of this number 1. Oh, dang it. I wrote the wrong. There, those 2. So I have 4 copies of this number 1, which means I only really take the rest of these. So if I look past those ones, I have 1, 2, 3, 4, 5, 6 leftovers, and I have nothing in the bottom. So down here, there's essentially nothing, right? These kind of disappear in a way. So then how could I write the simplified answer? Well, I'm left with x times x times x times x times x times x. And another way, or a simpler way of saying that would be x to the 1, 2, 3, 4, 5, 6. Okay, so that is the simplified answer. And of course, we should ask ourselves, okay, cool, but let's say that I had something like x to the 84th over x to the 17th. Am I seriously going to sit there and go x times x times x times x times x times x? No, that's going to take way too long, way too long, way too long. You're going to spend more time writing x's than you are solving the actual problem. So let's see if we can find a shortcut. So let's see. So is there a shortcut? Well, let's see. I ended up with a final answer of x to the 6th power. I started with 10 and 4. So if I think, if I start with 10 and 4 and I know that I end up with 6, well, how could I get 6 from the numbers 10 and 4? So think for a second. Could I do it with addition? Could I do it with subtraction? Could I do it with multiplication? Could I do it with division? Blah, 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 blah. And hopefully you will see you could do it by subtracting 10 minus 4. So that would give you the more straightforward way of getting the answer. So let me simplify this for you. Let's say we had x to the... Let's say we had x to the a power divided by x to the